Good afternoon.
So we are continuing chapter 2. So we went through last class. We went through the Fourier's law, the heat equation, and derived it for the Cartesian coordinates. So we have our heat equation down at the bottom here. We have it for the other coordinate systems, and then when we started simplifying it, 1D, no generation, constant properties, and we can simplify what we see here. And then we went to the boundary and initial conditions, which we talked about, and that's where we ended last time, where we had for time, we need one boundary condition, and then it's basically the initial temperature distribution. So whatever that temperature is at every location at time 0. So usually it's the same temperature throughout. Okay, and then the heat equation has second order in space, so in x direction, that's shown here. So that means we need 2 boundary conditions for it. So, and that's where we talked about the surface temperature being the same thing at same temperature at any time. It's always the same one, so that's a constant surface temperature one. We have constant heat flux, which means the slope, right? Because the heat flux is the same, so that means the slope on that boundary is always the same. Okay, if the heat flux is the same, that means this slope is always the same. And then we talked about, I think I labeled this 3 and then this 4, but we talked about 4 first, and that is an insulated surface or symmetry. And that's the case shown here is an insulated surface. Well, it's going to have no heat flux through it, right? So that at that location x is 0, if this is 0, then the right side has to be 0, which means the slope is 0. Okay, so we have a 0 slope right here. Okay, on an insulated surface for there to be no heat flux. Then the other thing, this is for insulated surface or symmetry. Okay, the other case that this would be is for, let's say, a wall, and this is being where x is 0, and let's say we have convection on the right side of this wall and convection on the left side, and then we have some energy generated inside. Okay, so at steady state, what's going to happen is you're going to get a temperature profile that looks like this. Okay, so it's supposed to be identical on the left and the right, with the highest in the middle, which gives us a slope of 0 at the middle location. So 0 again for our slope. So that also would happen if we looked at kind of a sphere and did it in the radial direction. Well, it's always radiating for that center point. So that center point, the R direction, has symmetry in all different directions of R then, because you're going to have the slope equaling 0 at that location of R equals 0. Okay, so that's the other one. That's actually an easy boundary condition for spherical or cylindrical coordinates, but it's one that students typically forget about when they're first learning about the heat equation. All right, so then the last one is convection, and that's just applying conservation energy at that boundary. So if we look at that boundary there at x equals 0, we have on the left side of it convection, on the right side of it we have our Fourier's law. Okay, so we have our Fourier's law, and then we have our convection. Okay, and that's the convection boundary condition. If we have convection on that surface, okay, the one thing that happens in this is the surface temperature changes. Let's say we applying, T infinity is much greater than the initial temperature of that plane wall. Well, that means then we're going to have initially a large delta T, okay, here, between basically the difference between this. And then as time goes on, that delta T is going to get smaller. Okay, so this gets smaller, which means then our dt dx at x equals 0 gets smaller, which means our slope gets to be a smaller number. this is changing, this has to change accordingly. Okay. All right, so here is thermal conductivity. Okay, this is in the Fourier's law. So we see the values of it, a nice range of seeing these different types of materials and how they change based upon those categories. It has kind of the range of the ideas of what they are. We have a bunch of property tables in the back of our book for these different kinds of materials: solids, gases, liquids, and thermal diffusivity is in the back too. So we already talked about that. Oh, I did want to bring up the boundary conditions. There's a table in the chapter. So this is table 2.2, which lists the boundary conditions. Okay, so that's a good table to kind of mark to make sure it's because it's inside your inside the chapter. All right, so when we have conduction, okay, what is our methodology to use? So we have this solid, we want to know what's going on with it. Okay, well, first off is, which we kind of skipped, but if you're doing any research with Dr. Stegan, you know, he deals a little bit more in the micro scale or nanoscale effects, so you might want to look at this. But then there's kind of a specialized kind of equations for those that you have to take into account when you have a microscale or nanoscale, so very small dimensions things, versus a macro scale kind of problem. Then we don't have to, you know, worry about as much. And then so step one is just understanding whether we got to look at kind of a special approach to it. That's within the chapter, which I skipped over. But then step two is, you know, appropriate form of the heat equation. So is it Cartesian? Is it cylindrical problem? Is it spherical? So we just pick which one, the coordinate system makes it easy to solve, right? And then we're using that heat equation to ultimately get the temperature distribution. Okay, so that is what the ultimate goal kind of really is of the usefulness of that heat equation, is to get the temperature distribution. Okay. So we can take this equation, let's say here, and if it was steady state, we could integrate it twice, right, and get a temperature distribution. All right, so now step three is we know our temperature distribution. So now we have how the temperature distribution is maybe as a function of x, right? Now, if we know that, we can apply Fourier's law, right? Because in the x direction, Fourier's law looks like this, right? Which this part is just the first derivative, okay? And that's powerful. So if we know our temperature distribution, we can just take the derivative to get the heat flux at any location throughout that material. All right, so then chapter 2 is really trying to understand the heat equation, the boundary conditions, heat flux. Chapter 3, now we simplify and we say, okay, we're just going to look at 1D steady state conduction problems. Okay, chapter 4, we end up skipping, that's 2D steady state. The reason being is there's only applied for for simple geometry. Okay, so otherwise most of the problems these days are solved using numerical analysis once you get beyond a kind of a 1D problem. So we'll be skipping that. And then chapter 5 is transient. So that's when we'll apply just transient problems. And we'll only do a portion of that chapter. All right, so let's do some quick examples. We have 2.43. Plain wall with constant properties and no internal heat generation shown in the figure is initially at a uniform temperature Ti. Suddenly, the surface at x equals L is heated by a fluid at T infinity having a convection heat transfer coefficient H. The boundary at x equals 0 is perfectly insulated. And then part A, and then they give us this schematic right here. And then it says part A, write the differential equation and identify the boundary and initial conditions that should be used to determine the temperature as a function of position and time in the wall. Okay. Part B is on a temperature versus x coordinates, sketch the temperature distributions for the following conditions. We have initial conditions, steady state condition, so that's when T goes to infinity, and two intermediate times, so two times in between initial and steady state. Part C is heat flux versus time coordinates. Sketch the heat flux at the locations x equals 0, x equals L. That is, show qualitatively how the heat flux at the x equals 0 and at x equals L varies with time. And part D is write an expression for the total energy transferred to the wall per unit volume of the wall. Okay. All right, so let's start and work our way through this problem. So part A, differential equation, initial and boundary conditions. Okay, so which may be used to find the temperature distribution. So we don't have to find the temperature distribution. We're just setting up what we would solve. Okay. All right, so our schematic now, if we take that wall and kind of, just take a section of it. Well, we have convection, all right, on the left. The temperature of that fluid is greater than the initial temperature of the material. So that means we're going to be putting some energy into the wall, right? Okay, so because now our temperature of that fluid is higher than the wall's temperature, so we're putting energy in. Okay, there's no energy generated, so we'll be changing the amount of energy stored inside here. Okay, so first off, they want a differential equation in boundary conditions. So that's where we just look for methodology. So we're not worrying about microscale and nanoscale effects. So then it's appropriate form of the heat equation to obtain the temperature distribution. Okay, so that means we got to figure out our heat equation. Okay, so if we go back to our general heat equation, we have one here. If we do 1D, so one dimension, so get rid of y and z. If we move k outside, that would be constant properties. And then it also told us no internal heat generation, so that term goes away too. All right, so then we can take that, the k that's outside, and divide it out, and we'll end up getting the form we created last class. That looks like that. Okay. So let's look at the problem. And you see, there it is. 1D conduction, constant properties. No internal heat generation. Okay. Then next is boundary conditions and initial condition. Okay, so initial condition, it's all at time of 0, it's all the same temperature. It's just saying at every location X, at time of 0, everything's all the same temperature. T initial. Okay, so we need two boundary conditions. So that was our initial condition for time, because this is to order of 1. Now we need two boundary conditions for X, because that's order of 2. All right, so we'll go back and look at this. So this is X equals 0 right here. Same with this. And this is X equals L. So that's our other boundary, right? So on the left side, at x equals 0, we see insulation. So, and on the right side, we see convection. So we go to our boundary conditions, and we see our insulated and convection. Okay, so we have our two boundaries conditions then. All right, so here we are. At x equals 0, it's insulated, adiabatic. At x equals L, it's surface convection or convection. Okay. All right, so then part B is the temperature distributions. They ask for, in these type of problems, we got to work our way through. We can't just throw this plot on the paper. We're not gonna understand it. It's asking for 4 lines. It asks for the initial condition. So our y-axis is temperature. Our x-axis is the x direction. So this is how temperature is changing through this wall, through this material. Okay. All right, so start off with, it says draw it for initial condition. Well, initially, it's all the same temperature. Okay, so then it's all initial condition is Ti. All right, so that's the first line. Then it says steady state condition when T goes to infinity. All right, so now we got to understand what's going on for that one. All right, so first off, what I like to do to understand this one is, all right, if it's steady state, the right side goes to 0. Okay, so then we're left with this when it's steady state. Okay, and we can integrate temperature twice here, and we would get temperature as a function of x. It's constant. One constant times x, second constant, and we're adding a second constant, and it would need 2 boundary conditions to get C1 and C2 at steady state. Well, we know then at steady state we're going to get a line, right? We know it's going to be a line, right? We don't know what that slope of that line is, right? An offset, but we know it's going to be a line. We see, the plot shows a horizontal line, but we need to figure out that. So we know it's a line when we have steady state because that's the equation we ended up with. All right, so then the other one to help us with that is if the left side is adiabatic, so this left wall right here, so that's where x equals 0, has a slope of 0. Okay, so always 0 slope. So then, all right, so that means the left side, the line starts off with 0 slope, and as we go across, it's still a line. It means we're going to be ending with a horizontal line for that end state. Okay, another way of thinking about that is we're putting energy in to our wall here. It's insulated on the left, so there's no energy leaving on the left. We're putting energy in on the right, and that energy that's being driven in there is from convection. Okay, so as we put in energy into that wall, surface temperature is going to increase, and it can only go up to T infinity. Okay, so eventually you're going to get that you are not putting in any more energy because Ts is equal to T infinity. So you get a horizontal line then. It's the right side. Basically, we have T infinity then. Okay, so all the way through, it's the same temperature. Then we need our 2 intermediate times, right? So they chose those ones you can draw at different times, but you want to kind of space them out. So these ones start with the first one here. We just kind of play it off with understanding the boundary conditions, what's going on, to determine how to draw the line. Well, the easy one that I like to first start off with is we know the left side has to be a slope of 0 for the temperature distribution. So we have slope of 0, slope of 0, slope of 0. Okay. and then the right side is from convection. Okay, so initially, we're going to have a large delta T. Okay, this is going to be large. So we're going to have then, if this is large on the right side of this equation, that means the slope has to, this dt dx has to be large. The slope has to be large, which is the slope of the temperature distribution, which is that is the slope right there at that point. So that is a large slope because we're putting in energy rapidly initially, or in the initial time, right after the initial time. Okay, so we have a large slope, and then it levels off to zero slope on the left. Then sometime later, right, the delta T is still greater than zero, but the slope isn't as high. It's not as high as the delta T, so this right side is not as high, which means the slope is not going to be as high on the right side. So now the slope on the right side is not as high. Okay, so we draw our line with a smaller slope, and then we end up with a horizontal on the left. Okay, so that is our 4 lines. So you have to kind of work your way through when you have a problem like this. Work your way through those lines. Okay. Questions?
Yeah, Professor, are we going to have more examples of how to draw these graphs later on?
A little bit, and then there'll be a homework problem with them too, at least one that will have these graphs to work through.
All right, thank you.
Mm-hmm. All right, so part C is so the biggest challenge here is it's the heat flux versus time. Okay, so the x-axis is now time. So now we're looking at the heat flux. So this is our heat flux on the right side, right wall, and this is our heat flux on the left wall. Okay, so we have our left wall is adiabatic, and our right wall has convection, right? So now we're looking at it not with location throughout the wall, right? We were looking at temperature versus location, right? And the last one, now it's heat flux versus time, right? And heat flux is this through the wall, right? It's from conduction through the wall at any location inside the wall. Well, if we're looking at the left wall, right, we have an adiabatic surface, so there's no heat flux through that wall. So that's the easy one in this problem. So we have a 0 all the way at any given time. The left wall's heat flux is 0 because it's insulated. And now the right side, the right wall, we have convection, right? So if we look at this, it's basically just looking at the right wall and how this heat flux changed with time. So initially, it was a very steep slope, very high. Then the slope got less steep, so a smaller slope. And then it was a horizontal line, sort of 0 slope. Okay. So if that's happening, we had our line then being high, steep slope makes a high heat flux, and then it gets smaller and smaller as that slope of our heat flux, right? So that's steep, lower slope, 0. Okay, so that's at time. Initially high, and so that's steep heat flux. That means less heat flux, 0 heat flux. So as time goes on, it was steep and it was some intermediate. And then it's 0 when it gets to steady state. Okay. Last one, part D, is total energy transferred to the wall per unit volume. So first we want an expression for the total energy transferred to the wall. And then we want it per unit volume. So we just divide by volume. All right. So if we look back at our problem, the energy in we have coming from convection. So our energy in is just from convection. Okay. So we write down that first. That's what you see here. Okay. And then we put in Newton's law of cooling and pulled the surface area and the convection coefficient out. Okay. And this is just that surface on the right side temperature. Now then it's the per unit volume. So now we're just dividing by volume, okay, which is the surface area times the thickness of this wall is the volume. Okay. So we divide on the left and the right, and things cancel, and we're left with our equation right here, and that's all they want us to solve. It's just that setup. Okay. Any questions? All right. Another problem, 2.29. The steady state temperature distribution in a semi-transparent material of thermal conductivity K and thickness L exposed to laser irradiation is of the form, and it gives this temperature distribution right here that you see on the slide. Tx equals negative A divided by Ka squared e to the negative AC or Ax, and then adding that all to plus B times X plus C. Okay, so we have our temperature distribution as a function of X given, where capital A, lowercase a, capital B, and capital C are known constants. For this situation, radiation absorption in the material is manifested by a distributed heat generation term, Q dot as a function of X. And then they give us this schematic right here. And then part A, obtain expressions for conduction, heat fluxes at the front and rear surfaces. Part B, derive an expression for Q dot as a function of X. In part C, derive an expression for the rate at which radiation absorbed in the entire material per unit surface area. Express your result in terms of the known constants for the temperature distribution, the thermal conductivity of the material, and its thickness. All right. So we have this semi-transparent material that has laser irradiation. So that's providing our heat flux in and out, but then also because it's semi-transparent, some of that laser radiation is basically energy generated within the material. Okay. All right, so, and they give us this temperature distribution. So for part A, they want expressions for the heat flux at the front and rear surface. So they want an expression for the heat flux right here, that top surface, and then for the bottom surface. So where would we start to get that? Where would you get that heat flux?
Can you repeat the question, Professor?
Where do we begin to get the expressions for the heat flux at the front surface, which is this, and then at the rear surface, which is this?
Energy equation?
The energy equation? Not even there. Okay, so all right, so let's take a look at our methodology here. All right, so if we step one, we don't have any microscale or nanoscale effects. All right, so step two shows the solve appropriate form of the heat equation to obtain the temperature distribution. So this one says heat equation to to obtain the temperature distribution. But do we have the temperature distribution in this problem?
Yeah.
Yeah, so they already gave us the temperature distribution, so we don't have to do step 2 in this one. Okay, so then we have 3, knowing the temperature distribution, apply Fourier's law to obtain the heat flux at any time, location, and direction. Okay, so that means Fourier's law, right? So if we look at Fourier's law here, okay, we have 1D, right? So how do I utilize this to get the heat flux at this top surface then?
You set x is equal to 0?
Yeah, first you got to take the derivative, but then yes, you set x equal to
Okay.
0. Yeah, so this is dt dx. So we first, basically, this is the same as that, right? So first we, it's like a star right there. First we take the derivative and then we plug in x equals 0 for the left side. Okay. All right, so that's what you see being done right here at the top. So we have Fourier's law, right? And if we take the derivative of temperature, our temperature distribution, that's what we get right here. Okay, so if we put this together, we have an equation for the heat flux at any location through that semi-transparent material. At any location, we know the heat flux then, just by that equation. All right, so at x equals 0 now, we just plug in x equals 0 into this equation, and it simplifies to this. Rear surface, so down here, that's where x, so this is at x equals 0, and then this is at x equals L. So now that's where we just plug in L for x, okay? And we get our equation right here. Okay. All right, so part B, the heat generation rate, Q dot, is a function of x. All right, so you see here the step that they're doing first off is basically the let's go back to our simplify, show that. We go back to our heat equation. So they had 1D, but we have generation. Okay. So we'll remove that cancellation. Constant properties, which gets us to pull K out. And then steady state. Okay, so that term goes away. So that's what we got right here. So now they're asking for the heat generation. So we just are solving for this. So you just see them rearranging the same equation. Okay. So how do we utilize this now? We have that equation. What do we do?
Substitute what we already, what we got from the first part.
Yeah, so we just basically dt dx gets substituted in here, and then we just take another derivative. Okay, so this is our right here, right? And then we take the derivative again and multiply k out, and we get our equation here. And we see that the volumetric heat rate is a function of x in this problem, okay? Because of what the temperature distribution has. So that's part B. Part C is expression for absorbed radiation per unit surface area. And there's two ways of solving this. So they want absorbed radiation per unit of surface area. So it's kind of looking back at the problem. If we look at this problem, we have some heat going in, we have some heat coming out, and then we'd be left with the difference would be energy generated if we're at steady state. All right, so if we think of that, we have energy in, energy out, energy generated, energy stored, and if it's steady state, that goes away. So then we just have energy generated equals to energy out minus energy, they do it the opposite. So energy in, negative energy in, plus energy out. All right, so we just go to our, what we did for part A. This is going in, the top surface, and the bottom surface is out. Okay. So we have here, heat flux, and we already solved for those right here. And then we have this, so we use those two equations. Heat flux in, this will be out, right? So in, out, plug it in, we get this. So the energy generated is the difference between those two because it's at steady state. So the energy, the excess energy that isn't in or out has to come from generated then. Another way of solving the same problem is in part B, we solved for the volumetric heat rate as a function of X. So at different locations of X, what that volumetric heat generation is as it goes through that material. And that's occurring because it's semi-transparent and we have laser radiation. So it's different at different points throughout this energy generated that's being generated at that point. So we could just take this equation and just integrate it over our length. So from x equals 0 to x equals L, just integrate all that, and you basically get then the total energy generated. And that's what you see here. So since the heat generation value is a function of x, we just integrate over x. And if you do that properly, you're going to get the same equation as above. So it's kind of two different ways of going about it.